Greetings of the day. I am Dr. Suja Alex. I would like to extend my gratitude to Dr. Meena Kadigari, ISER TVM, for this wonderful opportunity. It's a great pleasure and honor to present the research paper titled Deep Transfer Learning for Communicable Disease Detection and Recommendation in Edge Networks, which was published in IEEE ACM Transactions on Computational Biology and Bioinformatics. This research was a joint work done by Dr. Meena Kadigari, Dr. Abhishek Hasra, and Dr. Sudarshan Andy at different affiliations. Worldwide, considering the increasing number of COVID 19 disease cases, the early detection of the disease can prevent and limit the outbreak. To restrict the spread of COVID 19, it's essential to study the health parameters, including temperature, heartbeat, pulse, and oxygen saturation through various smart sensing technologies, including wearable sensors to analyze the monitoring data using advanced machine learning models with higher accuracy. The main research questions that are addressed for analyzing COVID 19 disease are how to design a smart healthcare framework in distributed edge network, integrating a set of wearable sensors and advanced machine learning technology. The second challenge was which type of lightweight machine learning model is useful for data analytics at edge networks that can predict the health parameters efficiently using minimum data with higher prediction accuracy and training time. Training a standard machine learning model and deep learning models for diagnosing COVID 19 disease require huge amount of monitoring data and computational resources. Due to the limited capacity of the resources in the distributed edge devices, the standard machine learning and deep learning models are unable to diagnose the disease using minimum monitoring data with a higher accuracy and minimum training time. The recent development of the deep transfer learning technique plays an important role in disease identification with minimum data and computational resources. Deep transfer learning transfers the knowledge from a well trained model to a new model that can run in resource constrained edge devices and diagnose the disease with a minimum training time. In this paper, they developed a novel edge centric healthcare framework that employs a set of wearable sensors in edge networks to monitor and analyze health metrics remotely using bag of neural network model and deep transfer learning. The primary objective of the proposed work is to optimize the accuracy of deep transfer learning enabled bag of neural network model in edge networks. These figures show the deep transfer learning enabled edge centric healthcare framework and the execution flow of the bag of neural network lightweight model. The proposed bag of neural network model is a population based neural network strategy for data classification. Bag of neural network model is incorporated into the proposed healthcare framework due to its good solution quality, quick convergence speed, and ease of implementation. Before processing, the data must be corrected and feature extraction must be performed to improve the data quality. Once data is filtered, the distributed edge devices perform data analytics based on the refined data using advanced machine learning models. Initially, The bag of neural network model is trained in the centralized server using synthetic dataset which consists of similar features extracted from the monitoring dataset. However, the pre-trained model is implemented to detect the disease using the selected features. After initial training on the synthetic dataset, a new lightweight bag of neural network model has been created using the deep transfer learning technique that can run in the resource constrained edge devices using small time series data with minimum training time and higher accuracy. The BYNN training process has two modes. In the first mode, the neural networks in the population perform the weight and bias modification based on the forwarding and backward error calculation, which is known as the backpropagation training. In the second mode, a transfer learning model is incorporated in the bag of neural network model that prepares a lightweight bag of neural network model by transferring the knowledge from the best performing neural network to other regular neural networks in the population. Hence, the first and second modes run parallel in the centralized edge or cloud server and the distributed edge devices. Finally, the appropriate authority is informed about the health status of each patient based on the report generated by the recommendation system. The population or the bag consists of a set of neural networks. These neural networks are considered as threads that were running parallelly. The proposed framework deploys each neural network as a lightweight process on distributed edge devices. The actual output of each individual thread is then calculated. The ith actual output of the neural network is a function of n symptoms trained on the layer S, which is again a function of three parameters. Here Pn is the nth pattern in the dataset. Ws and Bs are the weight and bias of the layer S. Next, the actual output is calculated parallelly for forward propagation. This parallel process is represented by this capital Pi symbol. The forward propagation process also includes the mean square error calculation of all the running neural networks. So here this EO1 is the error of the first neural network. This is for second neural network and this is the error of third neural network and so on. The calculated error is considered in the weight and bias modification. The modified weight is calculated by doing this derivatives of error with respect to the nth weight and C is the learning rate. Similarly, the modified bias is calculated by doing the derivatives of error with respect to the nth bias. The best performing neural network is identified based on the error calculation. The neural network with minimum error is considered as the best performing neural network. In this phase, a transfer learning technique is applied to transfer the knowledge from a well-trained bag of neural network model to a new lightweight model. The lightweight BYNN model reduces the dimensionality of the monitoring health parameters and performs disease diagnosis with improved prediction accuracy. The transfer of knowledge of the BYNN model is carried out by modifying the weight and bias matrix of regular neural networks in the population concerning the weight and bias matrix of the best neural network. The weight and bias matrix of the best neural network is calculated based on Euclidean distance between the regular neural networks in the bag. Here Wi best is the weight matrix of the best neural network. Bi best is the bias matrix of the best neural network. EU weight is the Euclidean distance of weight matrix calculated between Wi best and WNS. Here, WNS represents the nth layer weight matrix of the nth regular neural network of the bag. Similarly, EU bias is the Euclidean distance of bias matrix calculated between BI best and BNS. Here, this BNS represents the nth layer bias matrix of the nth regular neural network of the bag. Next, the difference between the weight and bias matrix of the best and regular neural networks is calculated. Here, gamma is a constant. The value of this constant lies in between 0 and 1. Next, the modified weight value and the modified bias value is calculated. Here, beta and rho are the constants which lies in between 0 and 1, and k is a random value between 0 and 1. So these two equations are used to modify the weight and bias matrix of a regular neural network model in order to generate a matrix that is very close to the weight and the bias matrix of the best performing neural network. The population size represents the number of neural networks in the bag. In minimum, there should be at least two numbers of neural networks that need to be considered. Figure 8 represents the overall evaluation of the proposed model with different population sizes. The experimental results of population size 20 and 30 achieved an accuracy of 98.7%. The population size 30 produces a better MSE value than the population size 10. Figure 10 shows that the MSE values for different learning rates observed, and the learning rate of 0.065 achieves a minimum MSE value of 0.04. In figure 12, different values selected for beta parameter, but the performance of the proposed model increased if it is fixed to 0.125 and the MSE value was 0.0722. In figure 15, the gamma parameter reports the minimum MSE value if it was fixed to 0.25, and at this value it achieved 92.2% of accuracy. In the comparative analysis, well-known classification algorithms such as decision tree, random forest, grid search, and XGBoost algorithms were used for the analysis. The proposed BONN model was performing well in terms of accuracy, precision, and recall. Thank you.